All right, class. Let's look at the rest of this page of mathematics. Here we have this thing that says exponent basics. What does this mean? This means, look, all we're asking for is, do you know what this is? X to the power of 4. What does this mean? It means the same as multiplying what? X times 4? No, that would be incorrect. It would be the same as X times another one, times another one, times another one. Look, 4 of them. How many? 1, 2, 3, 4. Does that mean that we write a 4? Not beside. That would only be... Because look at this. What is this? What if it was a number? We put 4 to the power... Oh, not 4. That's too many 4s. 7 to the power of 3. Is that the same as 3 times 7? No. Not good enough. Not the same. 3 times 7 is only 3 sevens. So we have like 7. 1, 2, 3, 4, 5, 6, 7. We have 3 of them. Look at this. 1, 2, 3, 4, 5, 6. Well, there's another stack. Okay. 1, 2, 3, 4, 5, 6. Okay. There's our 3 sevens. Is that the same as 7 times 7 times 7? No. That is only 3 times 7. 3, 7. What if we had 7 times 7 again? Then we would have... 1, 2, 3, 4, 5. This would be like 7 times 7. And then if we did 7 again, we would make it 3-dimensional because this diagram is failing to make any sense. Oh my goodness. Too many lines. Look, the important thing is, this is not the same. No. 7 cubed would be 7 times 7 times 7. Totally different numbers, you silly people. Okay, look, you tell me this, that's good. I am happy. Here we go. Polynomials. What is polynomial? Polynomial means we are adding up a bunch of things. What are these things called? They are called terms. That is what they are called. What does terms mean? Terms mean things multiplied. Or maybe just a number. That counts. That's a term. It's good. All right, so polynomial means you add or maybe subtract. Pretend you're adding negative number, whatever. You're adding a bunch of terms. Here's term, 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 another term. Okay. When we are trying to put these together, we do not know what x is, but we do know that x is not changing. It is one number, whatever the number is. We do not know. We're not going to find out. We're not that interested. We can't find out. It's not an equation. Okay. So what we have? Well, we know that x, whatever it is, it's the same number there. This is this. Okay, this and this are the same kind of thing. We have 3 times that number. We have 11 times that number. And then we put them together. Well, if I have 3 of this, and then I have 11 of this, how many of them do I have? Not that surprisingly, I have 14. Okay, 14x. How many x's do we have here? 3 of them there, 11 of them there. Put them together, 14 x's. Okay, that's good. We got that taken care of. I'm going to cross them off so I can't forget. Okay, what about this? Are x squareds the same? No, I do not know what x is. X squared is probably not the same number as x. And I don't know how many of the x's make up an x squared because I do not know what the number is, so I cannot put them together. They will be different things. So I will look instead at this. How many x squareds do I have? I got 4 here, 2 here, and then I take away 1. Okay, so this is 4, and 2 is 6. Take away 1 is 5. 5 x squared. Look at this. This 4 is all by itself. Nothing to combine with. Maybe if I had some other numbers in here with no x's, I would combine them. But it is all alone. We will leave it just the way it is. It is satisfied with itself. There we go. So the key here is to combine like terms. There we go. What do we mean by like terms? It means they're the same kind of thing. These ones were the same kind of thing. These ones were the same kind of thing. They come together. You can put them together in the same pile and share them equally amongst you and your neighbors in this good Soviet Republic. Let us verify if the shapes are to scale. This is the last question on this page, and then I will add a little something more. Let's make this... Oh, my zoom is out of control. Here we go. What does this say? Oh, camera. Camera. There we go. You can do it. Now, these numbers are rather tricky. Oh, they're not... This one's not too bad. Look. This is 11. This is 22. How does... If this is a scale diagram, scale diagrams are always about multiplication. Let's write that word down, multiplication. Okay, so that's important to remember. You don't add numbers to get from here to here if you want it to stay a scale diagram where the proportions are the same. Okay, so this perfect proportional thing, is it perfect? Let's find out. If I am going from... Just to keep my brain simple, I'm going to say from 11 to 22. Could I go from 22 to 11? Yes, but then it's getting smaller and I'd have to multiply by a decimal number or something. Look at this. We can just say multiply by 2. Okay, if this is done correctly, then I should be also multiplying this by 2. But what would I get if I do this times 2? Let's find out. 38 times 2. I don't feel like grabbing a calculator. I'm going to just write this down and try to be fancy. Here we go. 16. 3 times 2 is 6, plus extra 1, 76. Look at that. Glorious. Just like the glorious Soviet Republic. I don't know. Look at this. This is perfect. If this is the same as this, that means this is perfect. Perfect scale replica. Completely indistinguishable. This is the good, well, I mean replica. I mean it's a scale, and maybe I should not say replica. It is larger. Perfect scale enlargement. There we go. How do I know? You would have to write something down. I've been talking enough. I am not going to write it. I am going to just stop this video and then show you one more thing.